In this video, we're going to work example problems where we test series for convergence or divergence using the ratio and root tests. Now, before we get started, just remember that the ratio and root tests, what we're testing for in this case is the ratio and root tests are going to tell us if this given series is absolutely convergent, either that or divergent. And we know that any series that is absolutely convergent, that also means that the series is convergent as well. So just note that these tests are associated with absolute convergence, right? Which means that if you have a series, we know that if you have a series and you analyze this corresponding series, the series with the absolute value of the a sub n's, if this series converges, then that means this series converges. That means this is absolutely convergent, which means that it converges. Okay, and so that's what technically the ratio and the root tests are going to tell us if a series is absolutely convergent. If it is, then that means the original series is convergent. Okay. All right, so these initial problems, we're going to use the ratio test. So in the textbook, for these first 7 or 8 problems, it says to use the ratio test to determine whether the series is convergent or divergent. So they're telling us to use the ratio test. Okay, so what we do is, with the ratio test, we're going to get a new sequence formula that's given by the absolute value of a sub n plus 1 over a sub n. So here's a sub n, right? We're going to take a sub n plus 1 and divide that by a sub n, and then take the absolute value of all that, and we're going to get another sequence formula, and then we're going to take the limit of that sequence. Okay, so this is 5 to the n times 5 to the first, so what we're left with, so we got 5n over n plus 1. Okay, well, as n goes from 1 to infinity, this is always positive, so we can just remove the absolute value. Okay, so there is a sub n plus 1 over a sub n. And so this is a new sequence formula. Now what we do next is we find the limit of this sequence, not of the series. Note that, right? We're not putting this into a series. We're saying what's the limit of this sequence. So what's the limit as n approaches infinity of n plus 1 over 5n? So what we do here, we know how to evaluate a limit like this. We divide the numerator and denominator by n. Now, plugging in n, this goes to 0, so we're left with 1/5. Okay? So what we do is, the limit as n approaches infinity of a sub n plus 1 over a sub n is 1/5. And for the ratio test, what you do is you see, is this limit value less than 1? It is. So that means that this is absolutely convergent, which means that it's convergent. Okay, now this also ends up being a test for divergence. If this was greater than 1, then it'll tell us that this is divergent. If it's equal to 1, it's inconclusive. But okay, so here we see that this is convergent. Okay, ratio test. When we think about the absolute values, so looking at this, it's like when you take the absolute value of a sub n of this goes away, and then this is always positive going from 1 to infinity. So we've got okay, so let's do this. We can remove the absolute value because this is always positive, and we're not including this minus 1 to the n minus 1. So we've got, all right, a sub n plus 1 times, and then okay, so we're left with, so this is 3 to the n times 3 to the first, so the 3 to the n's cancel. 2 to the n times 2 to the first, so this 2 to the n goes away, and we're left with just a 2 down here. Okay, so we can, to make this easier to visualize, we can expand this. Okay, let's do this. N plus 1, and then we've got n squared plus 2n plus 1. Okay, so we've got 2 n cubed plus 2n squared plus n plus n squared plus 2n plus 1. So that's going to be n cubed plus 3n squared plus 3n plus 1. Okay, that's 2n cubed plus 6n squared plus 6n plus 2. And then, okay, so there's the absolute value of a sub n plus 1 over a sub n. So what is the limit as n approaches infinity? Okay, so we can see here, we know that since the order of the numerator and denominator are the same, if you divide the numerator and denominator by n cubed, both by n cubed, you're going to get, this is going to go to 3/2. That's greater than 1, so this diverges. Okay, let's use the ratio test again. And as far as the absolute value goes, this is never negative, k factorial. All right, so we can just take out the absolute value, and we've got, so one over k plus 1 factorial, and then we're dividing by a sub n. So, okay, now we can rewrite this as k plus 1 times k factorial, right? Okay, so all right, so what is the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n? This is equal to 0, which is less than 1. So that means that that's telling us that this is absolutely convergent, but any series that's absolutely convergent is also convergent. Okay, so we're going to just use the ratio test again. For these problems, we're not looking to see if the ratio test is applicable or trying to decide if we should use it or not. They're telling us we're just practicing the ratio test here, the mechanics of it. So they're telling us to evaluate this using the ratio test. Okay. As far as absolute value is concerned, it's like exponentials like this they're always positive, even if you had a negative value in the exponent. But here we're not even going to have negative values. N plus 1 is not negative, so okay, we can just remove the absolute value, and so we're left with, we're going to have n plus 1 is n plus 2. 2 times n plus 1 is what? 2n plus 2 plus 1, 2n plus 3. 4 to the 2n plus 3, and then 10 to the n plus 1. Okay, now we've got okay, and so we can do this. we've got 4 to the 2n times 4 cubed. Then we've got 10 to the n times 10 to the first. Then we've got n plus 1, 4 to the 2n times 4 to the first. And then 10 to the n. Okay. So here, this ends up being 4 squared. These two cancel. And so we've got 4 squared is 16. Okay, divided by 2 is 5. Divided by 2 is 8. So you've got 5 times... Okay. So we can take out this 5/8, and we've got the limit as n approaches infinity of... Okay. This n plus 1 over n plus 2 is going to... That limit is equal to... So, okay, this is 5/8, and we've got dividing the numerator and denominator by n. You've got 1 plus 1 over n over 1 plus 2 over n. So this is 5/8 times, this limit is 1. So 5/8, that's less than 1. So this is absolutely convergent, meaning this is convergent. Okay. So now here we have to think about what the absolute value is going to do. So we can, all right. This is, so, okay, this is minus 1 to the n minus 1. Right? Because if you've got a to the b, c to the b, that's equal to ac to the b. Right? Okay, and so now if we bring this into like the numerator, we get okay, now for going from 1 to infinity, this is always positive. So therefore, the absolute value of a sub n is just this. So we can for this, we could just remove the absolute value and divide, a sub n plus 1 by a sub n here. So, okay. We've got n plus 1, pi to the n plus 1, and then 3 to the n plus 1 minus 1 is just n, 3 to the n. Then we've got 3 to the n minus 1. That's 3 to the n times 3 to the minus 1. And then n pi to the n. Okay, so, and then this is pi to the n times pi. So, okay, we've got n plus 1. And then, so we got pi times n plus 1. Okay, and then we could bring this 3 into the denominator. These cancel here. Let's do, yeah. So 3n. So we've got pi over 3 times n plus 1 over n. So, okay, the limit is, we could take out the pi over 3 as n approaches infinity of n plus 1 over n. This limit goes to 1. Pi is about 3.14, which is greater than 3, so convergent. Or no, I'm sorry. 3.14 is greater than 3, so this is greater than 1, so divergent. Okay, here I don't think they want us to do like cosine of n plus 1 times pi over 3 divided by n plus 1 factorial, and then divide that by, I don't think they want us to do it that way. I think they're, because in actuality we wouldn't do it that way. If we could like use any method we wanted to, we wouldn't do it that way. So what we would do is we would say, so when you think about the general test for absolute convergence, if we determine that this series is convergent, so n factorial is always positive, so if we determine that this is convergent, that's the absolute value of this entire expression, but I just didn't put the absolute value on the n factorial, then that means that this is convergent. And if you remember when we did comparison tests, the fact that we can analyze the absolute value, it helps us with comparison tests. Because sometimes with the comparison test, the fact that we had when we had cosines and sines and they could be negative, it was kind of a pain to make a comparison. But since we can restrict this to, instead of, normally cosine would be between -1 and 1, but now we can say it's always between 0 and 1. Okay, so again, we're going to focus on this series here. If we can determine this is convergent, then we've answered that this is convergent. So we can think about the series. So let's do 1 over n factorial. It's going to be our comparison series. And I'm going to use 1. We can say that this is going to be always going to be greater than this and you might say, well, wait, can't this be equal to 1? I don't think when it comes to, if n was an x, then yes. But I think with the fact that it's n is an integer, I don't think it'll ever be equal to 1. So we've got pi over 3, 2 pi over 3, 3 pi over 3 is pi, which is 1. That's 1. So, okay, never mind. Well, we can do this, though. Remember, with comparison tests, we're really flexible when it comes to what we bring in to compare. Let's do this. Okay, and so if we could determine that, remember how comparison tests work, if we could determine that this is a series with this as the a sub n is convergent, well then since these terms are always greater than these terms, right? Because remember, 2 is always going to be greater than 1. That's the highest this can get. And that makes this convergent. And now to test this series, we're going to use the ratio test. And I think that's what they were going for. It would be stupid to do like cosine of n plus 1 pi over 3 divided by n plus 1 factorial, all that divided by cosine of n pi over 3. I mean, I don't think they were wanting us to do that. Okay, so ratio test on this, right? We've got the sum from n is equal to 1 to infinity of 2 over n factorial. So, and just to point out, we could just take the 2 out, right? And then if this is convergent, then whatever it converges to, just multiply that by 2. So, all right. A sub n plus 1 over a sub n. And so this is n plus 1 factorial times n factorial. So, all right. Now the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, but we don't need an absolute value here. So is equal to 0. That's less than 1. So this is convergent. And then by the comparison test, this is convergent. And then that means this is absolutely convergent. So that means this is convergent. Okay. So yeah, this is always going to be positive for all n. So, okay, we don't need to worry about the absolute value. So we just remove the absolute value, and we've got n plus 1 to the 100 times 100 to the n plus 1. And let's go ahead and change this to 100 to the n times 100 to the first. Just 100. Okay, n plus 1 factorial, which we know is n plus 1 times n factorial, because we know these are going to end up canceling. So, okay, so we've got n to the 100 times 100 to the n, and then n factorial. So, okay. What we're left with is n to the 100 okay, and then this, we get this. So 100 okay, so this as a limit. So okay, 100, and then the limit as n approaches infinity. Okay, yeah, we can evaluate this, and the way we do this is, so what you can imagine is if we expanded this out, we would get some enormous polynomial that's of order 99. So that with that, we would divide the numerator and denominator by n to the 100. And so what happens is you get 1 in the denominator, and then everything in the numerator is going to be, every term is going to be divided by at least n to the first. So as n goes to infinity, the numerator is going to go to 0, and this is going to be 1. So this limit goes to 0. 0 times 100, this goes to 0. That's less than 1. So convergent. All right, so what is looking at this, what's the a sub n? Well, okay, 1 times 3 times 5 times 7. Well, okay, this is the a sub n. You can't really, this is it. So we need to, if we think about the absolute value, we could just drop the minus 1 and the n minus 1, and this is always going to be positive. And so we could just write it out just like they show it here. So a sub n plus 1 is going to be, so let's see, we've got 1 times 3 times 5, and then 2n plus 1 minus 1 over n plus 1 factorial, which is n plus 1 times n factorial, and then times 1 times 3 times 5, and then 2n minus 1. Okay. Now, the 2n plus 2 times n plus 1 minus 1 is 2n plus 1, right? So, okay, now, so what we can think about is we've got 1 times 3 times 5 times, and then 2n minus 1 times 2n times 2n plus 1. Okay. And then here, 1 times 3 times 5. Okay, so all of this cancels, right? So you're left with 2n times 2n plus 1, and then, all right, so we've got 4n squared plus 2n. There we go. So the limit as n approaches infinity of and this is going to go to 0. Right? Because the order of the numerator is higher than the order of the denominator. So this is convergent. Okay, similar type of problem. Now this is always positive, so we can just remove the absolute value. So we've got 2 times 4 times 6, and then 2 times n plus 1. So that's 2n plus 2. Okay, over n plus 1 factorial, which is just n plus 1 times n factorial. And then we've got n factorial, and then 2 times 4 times 6. Okay. So we've got 2 times 4 times 6, and then 2n plus 1, 2n plus 2. Okay. So all of this cancels, and we're left with okay. Well, now this is actually going to simplify, because if we factor out a 2 here from the 2n plus 2, so we're left with 2 times 2n plus 1. So we can take the 2 out front, limit as n approaches infinity. 2n plus 1 is equal to infinity. So that is greater than 1, right? They said, okay, it either converges to something greater than 1, that means the series is divergent, or it converges or diverges to infinity. So this is divergent. Okay, now we're going to work a few problems where the textbook tells us to use the ratio test. Okay, the ratio test, what do? Well, remember, this is still telling us about whether or not a series is absolutely convergent. So it's that same type of idea. We're looking if we can determine that the series is absolutely convergent, then we can say it's convergent. And so the absolute comes into play where we're going to take the absolute value of this a sub n, right? This entire a sub n, and then put that under an nth root. And then we're going to be taking the limit as n goes to infinity of that. So, all right, the absolute value of this, there's no need to use the absolute value. This is always positive. So, okay, we've got the nth root of the absolute value of a sub n. So the nth root of the absolute value of a sub n is n squared plus 1. Okay, so now it's the exact same idea as the ratio test. You take the limit as n goes to infinity you find the limit of this sequence. If it's less than 1, if it converges to something less than 1, then it's absolutely convergent. So okay, here we've got the same order in the numerator and the denominator, which means that this is going to go to 1/2. That's less than 1. So this is convergent. Okay, the absolute value of this, so the absolute value of a sub n would be, we can just take this out, it should just be this. Yeah, because this is always positive. Okay, now well, you notice though, we could write this like this. Therefore, the nth root of the absolute value of a sub n is 1 over that natural log of n. So what is the limit this is equal to 0. That's less than 1. Convergent. Okay, so as far as the absolute value, this is always positive, right? Now, I think I see where they're going with this. So, okay, so this a sub n, the absolute value of this a sub n, we don't have to worry about the absolute value. There's no negative to deal with. But, okay, we can write this way. Right? Based on properties of logarithm or properties of exponents. Okay, so in that case, the nth root is okay. Now, when we take this limit of this sequence here, the technical way you're supposed to do it is when you're evaluating the limit of a sequence is you replace n with x. And if there's no issue, this is one of the ways you do it. There's no issue here as far as like you don't have a function that doesn't work with the continuous variable. There is no issue. Then you go ahead and take the limit as x goes to infinity of that. And whatever that does, the sequence does. What is this limit? 1 plus 1 over x to the x power. You should try and remember this. Should try and sear this in your brain. What is this limit? This is e. This is the definition of e. And if you had the limit as x goes to infinity of 1 plus 2 over x to the x, this would be e squared. This is e to the first. Okay, so but that means that this limit, that means the limit as n approaches infinity of this is equal to e. That's greater than 1, so this is divergent. Okay, for these last few problems, what we want to do is we're going to use any method we want to determine whether the series is absolutely convergent, conditionally convergent, or divergent. So any method, not just the ratio or root test, any method we want. So these are more about, we want to think about the idea of absolute and conditional convergence, because that's what this section is about. It's not just the ratio and root test, right? It's also about that idea of absolute and conditional convergence. So, all right, if we look at this, anytime you see an alternating series, and then you can test it any way you want. Yes, I mean you think about the possibility of the ratio test. It has an absolute value in it, right? But I would think you should go to the first thing you should think about is the alternating series test, right? It has the name alternating series in it. However, just a reminder that the alternating series test wasn't for absolutely any alternating series. The alternating series had to have that it had to be the b sub n term had to be decreasing. So if you go to the alternating series test and the series you have doesn't apply, then you could go to the ratio test. But okay, so we look here and we see that the b sub n, like if we take the absolute value of this, we get the b sub n, and that is going to be 1 over the natural log of n. All right, now so the requirement to be able to apply the alternating series test is that these terms need to be decreasing. Every successive term needs to be smaller than the previous, starting at some n value. It doesn't have to be 2, but it looks like even starting at 2 and going to, okay, 2, starting above e, which is 2.7 something, this is always going to be decreasing. I think going from 2 to 3, this would increase. But then after n is equal to 3, this would be decreasing. So we can use the alternating series test. And so all we do is we take the limit of the b sub n. Not the series, just the b sub n. So it's nice. And that's going to be 0. And so therefore, this series is convergent. All right. So what does that mean? Well, okay, we know this is convergent. But remember, there was cases where we found alternating series that were like the harmonic series, for example. The alternating harmonic series is convergent, but the harmonic series not alternating is divergent. So that's where the conditionally convergent comes from. So to see if this is absolutely or conditionally convergent, we want to analyze this series. The absolute value of that a sub n. If this is divergent, then this is conditionally convergent. If this is convergent, then this is absolutely convergent. Okay, so if we think about 1 over n, how is n related to natural log of n? Okay, so there's natural log of x and there's x. So x is greater than natural log of x. Okay, so n is going to be greater than natural log of n. So it's going to be like this, because the term we're talking about is in the denominator, right? This is always less. That means this is greater. Okay, now with that, the series, this is the harmonic series, this diverges, but these terms are always less than these terms. So that means this diverges based on the comparison test. We just did the comparison test. So therefore, since this diverges but this converges, then this is conditionally convergent. Okay, so just looking at this, my mind goes to the ratio test, but we're going to talk about strategies for how to approach analyzing you're given a random series and how to, and you can choose any test you want. How do you choose a test? But let's see the absolute value of this. You can see we can take out the minus 1 to the n, and we're left with 9 to the n over n times 10 to the n plus 1, and that's always positive. So the a sub n plus 1 over a sub n, we can just think about this with the minus sign gone. And so we've got 9 to the n plus 1 is going to be 9 to the n times 9 to the first. And then we'll have n plus 1. And then 10 to the n plus 1 is, okay, so that's 10 to the n and 10 squared. Okay, then we've got n, 10 to the n, 10 to the first, and then 9 to the n. So all right, we're left with 10. Okay, so the limit as n approaches infinity, we could take out that 9/10 of the absolute value of n plus 1, of a sub n plus 1 over a sub n is equal to 9/10. So, and we can see that this limit goes to 1, so this is less than 1. So, okay, so what does this mean? Well, to answer this question, it's nice when we use the ratio test or the root test, because the ratio test or the root test, but okay, we're talking about the ratio test here, but what this means that this is absolutely convergent. That means the absolute value, the series of the absolute value of this is convergent. But if that's the case, then that means the series is also convergent. Like there's never going to be a case where you have the absolute value of the a sub n of a series that series is convergent. The absolute value series is convergent, but the actual series itself isn't. That's never going to be the case. If this series is convergent, then that means that the original series without the absolute value, that's absolutely convergent. And that tells you that the original series is convergent. But it could be the case that you have the original series be convergent, but this series is not. And that's what's called conditionally convergent. All right, so yeah, the root test here for sure. And again, the root test is nice because it's going to tell us about the if it's absolutely convergent. It's like with the alternating series test, it only told us that the alternating series was convergent. It didn't tell us about that corresponding absolute value series. These are telling us straight up about both the absolute value and the actual series. So, but here we can see the absolute. There is no absolute. Like this is always positive going from 2 to infinity. So we can just remove the absolute value. Or no, we're going to do the root test. So okay, the absolute value and then the root is just going to be n over natural log of n. Okay, and note that with the ratio test, we don't have to, or the root test, we don't have to check if this is like decreasing or anything like that, like we had to do with all the other tests. It doesn't matter if this is decreasing or not. So okay, we take the limit as n goes to infinity of n over natural log of n, and so okay, we're taking the limit of a sequence, and so looks like we can use L'Hopital's rule, but you don't use L'Hopital's rule on these n's like this. So let's say if we replace n with x, is this valid? Yeah, that's fine. So okay, let's take the limit of this series or this sequence. Okay, infinity over infinity. So let's use L'Hopital's rule. So you've got 1 over x is just x. Okay, so the ratio and the root test, if this limit, so yeah, this limit is equal to infinity. If the limit of this sequence is converges, but it's greater than or equal to 1, it's greater than, no, okay, if the limit of this sequence converges, but it's greater than 1, or it diverges to infinity, then that means that the original series is divergent. Okay, so we're not going to do any ratio or root test here. I mean, I guess we could try it. Okay, let's look at the absolute value series. That's going to be it's going to be arc tangent of n over n squared, and this is the absolute value series because going from 1 to infinity, if we look at, there's arc tangent of x. So when it's always positive when x is greater than 0. So this is the absolute value of this a sub n is this. All right, so is this convergent or divergent? Well, we could say 1 over n squared is always going to be less than arc tangent of n over n squared. And so if we come back here, so here's 1, but then so at n is equal to 1, that's not the case, but n is equal to 2 to infinity, that's the case, which is that's fine. Okay, so this is true. We know though that this series converges, but this is always less than this, so that doesn't tell us anything. But remember, when we talk about comparison tests, you're very, very you could be very flexible with this. Why don't we do this? Let's just put whatever number we want up here. 10. Okay, now with that we could switch the sign. Now, is this true? So is 10 always greater than arctangent of n all the way to infinity? Yeah, arctangent, it has a vertical or a horizontal asymptote. It's like at pi over, I forget what it is, pi over 4 maybe, but definitely less than 10. So going off to infinity, this is always greater than this. Now you might say, well, how can we put a 10 there? Think about it, okay? The going from n is equal to 1 to infinity, what is this equal to? So what does this mean? Well, this is convergent, right? What does convergence of a series mean? That means it equals to a finite number. Like, let's say it's, I don't know, 6. Okay, so what is 6 times 10 is 60. That's what, so that means it's, so since this, we know that this is valid, take that 10 out like that. So both this and this are equal to 60. I mean, this is convergent. That should make sense to you. All right? This is convergent, and this is always, these terms are always larger than these terms. Now, you still might be a little confused by that because it's almost like, well, we could do anything we want here. Like we could make any series convergent. I could make this 5 billion for some other comparison test. Okay, the key was that what allowed us to do that just now was that it was predicated on the fact that as this goes to infinity, we get a finite number. That's the key. Normally that's not the case, right? You might have n and just n up here. That goes to infinity. Or you have something that's not, it doesn't behave that way. Right? The key was that we had matching n squareds here, and you can look at this as like a finite number, just like 10 is. That's how that worked. Okay. So all right, this is convergent, and the terms here are always greater than the terms here. So that means this must be convergent. Okay, so what have we just showed? We've just showed absolute convergence. Right? Because if you take any series and you evaluate the corresponding absolute value series, if that's convergent, then the original series is convergent, or also called absolutely convergent.